Okay, thank you. I first introduce myself again. It's a pleasure to be here today at Online DOE Summit 2022 to present my work Untitled Application of Design Expert in Classic Aromatic Nitration. The choice for the aromatic nitration reaction was due to amount of existing information and the challenge of seeking an improvement in selectivity of a particular isomer in apparently consolidated process. Thus, is it clear that I motivate by the search for continuing improvements of chemical process. For this, it's necessary to know the problem and its impacts to propose hypotheses can solve it. Thus, I use the experimental design to assist in this reengineering process using Design Expert. Among the various steps to be carried out, I slightly identify change levels as a decisive steps for obtaining good results. However, how to do it? First, it's necessary to look at the anatomy of chemical process. There are many interconnect steps, all of them fundamental to guarantee the quality of the products. So which stage choose? I suggest to focus on the reaction stage because I think this is the most important and it directly affects the subsequent steps. For example, the separation method used depends on the reaction medium and the properties of the products involved. In the purification steps, the existence of byproducts that needs to be isolate. This can make the process more complex and involve a higher cost. Therefore, the reaction stage needs to be optimized for the process to be commercially implemented. But is this true? There is any change of identifying significant improvements in apparently consolidated process? Yes, I think this is possible. In fact, I can show you how to proceed by giving you examples that confirm this statement. I developed a methodology combining tools already available, wherein the focus is on the reaction stage of the process, associating the existing chemical knowledge, though, and then cycle tools. The steps involves identify and study the problem and define the objective variables and study ranges. Then you can plan factorial design complete or factual depending on the number of variables under the study, and you execute the experimentals as planned. You have to do a critical analysis of experimental and statistical results to determine the influence of variables and adequacy of study ranges, completing the first cycle of screening. The objective of the cycle is to ensure the proper choice of variables and especially other studies ranges. This information is used for the steps of the second cycle of modeling, which begins with the application of the responsive surface method, following by running the experiments as planned and do a critical analysis, the experimental and statistical results. And the question is asked, is there a valid model to represent the experimental results? If the answer is no, you must return to step 7 and carry out a new planning. If the answer is yes, the software's numerical optimization tab is used, filled with specific criteria to identify the best results that will be validated and implemented as an improvement in this process. Thus, In the application of this methodology, it's possible to propose models that describe the influence of variables and their interactions. And yet, with this information, establish process improvements through the identification of more selective and optimized areas. So, I will use case study 1 to exemplify the application of this methodology. As explained above, it involves a nitration reaction to obtain the per-nitrobenzene product, which is obtained together with these ortho and meta isomers and some polynitrate products. The product of great interest is the para-isomer. It used for the production of commercial azo dyes and other organic products such as pharmaceuticals and photochemicals. The best conditions report yields in order to 75% and selective in order 2 moles of para-isomer to 1 mole of ortho-isomer. Selectivity is very important in this process because it directly impacts the separation and purification steps. It is mentioned that these steps are hard and involve distillation and successive crystallizations. To improve selectivity, catalyst replace can be suggested, but I believe that catalyst replacement can be very costly to this process. Thus, I was decided to apply the developed methodology, keeping the original catalyst. The objective is to identify the surface to represent the process, and after optimization, the best results, as you can see in this hypothetical example. There are 2 maximums. The idea is precisely to seek this area of the best results. So, applying the methodology, first I define 4 responsible for 4 variables that I believe are responsible for providing better results. They were temperature, time, nitric acid to substrate ratio, and sulfuric acid to nitric acid ratio. The range shows depends on the substrate. Unfortunately, I cannot divulge the actual values of these studies intervals, and I will use all of them coded here. The responses were total yield, isomers yields, and ratio of isomer to orthoisomer. When I plan factorial analysis, I obtain these results. Although the proposed model explains the results very well, as seen in this graphic of predict values by actuals, it cannot be used, as you can see in this interaction graphic. Here, the path of curvature is very clear. So the center points are not part of the generate linear surface. Then, following this scheme describing this methodology, new experiments were planned using the responsor surface method to enable the generation on non-linear models. A reduced scenario obtained for response surface of the 2 most important responses is present here, only showing the values of the individual variables. Interaction are part of the final model, but for confidentiality reasons are not shown here. It can be seen that it's possible to obtain statistical models for the 2 responses, as can be seen. So the p-value here and here, except these 2 variables, and for the good correlation coefficients here and here. For this case in study, it's observed that the student's range in all variables promotes significant changes in the total yield, which does not happen for the selective to obtain the para-isomer like these two variables. Here, the chance in the time and the ratio values between sulfuric acid and nitric acid in the range under study did not cause a significant change in the para-isomer selectivity, but is important for the total yield. As can be seen from these graphics, total yield has three options with values above 75%. However, these options do not desire increase the selectivity, but is an option with para-ortho selectivity of 14:1 with a total yield of 72%, which I think is viable options. And other options, as you can see in the next slide. It was obtained 92% for total yield, but with the selectivity to ortho isomer, and two other conditions with selectivities for the para-ortho isomer ratio well superior to the 2:1 reported. But no positive change in the total yield. Thus, I decided, after obtaining the model for each answer, perform the numerical optimization. Defining as criteria the highest total yield, the lowest amount of ortho isomer, and the maximum of para isomer and ratio para ortho isomer. These result in a final total yield of 88% with selectivity of 50 moles of para isomer to 1 mole of ortho isomer. Now, for the commercialization of para isomer, it is only necessary to filter the reaction medium, allowing the elimination of purification steps and reducing product costs. Based on the good results, I decided to apply this methodology for the nitration of other aromatic compounds. So, following the same reason, I performed the nitration of bromobenzene. The product of interest is para-nitrobromobenzene, which is a common intermediate for a production of variable industry compounds, including intermediary of rubber. Using the same type of synthesis, the report yields is 79% with 3:1 selectivity of para-isomer over to ortho-isomer. Again, I applied the methodology and performed the two-cycle proposed. First, I can use the factorial analysis, and the results confirm, like you see here, to need to use the responsive surface method to generate models value due to observe these curvatures. Even so, we can see situations with a maximum total yield here associated with high values of para-ortho ratio. We can see the results of the response surface methods, and again, all individual variables influence the total yield, but only the values of the molar radius are decisive for obtaining the best para-ortho ratio, as example here. In the two exemplary conditions, the conversion was almost quantitative, with the total yield increasing from 79% to 99.8%, as you see here, and selective increase for 3 to 1 for 14 or 18 to 1 in this case. So it's not necessary to carry out the numerical optimization. So we can conclude in the preliminary way that the two substance studies of being weak disadvantages for the nitration reaction, which is an electrophilic aromatic substitution reaction, and that the results for them were positive, but with different influence for the same variables in the study. Then we can ask, will we be able to obtain positive results in nitration involving other strongly activation observing substrate? Future case studies can confirm this. First, I present you para-nitrophenol, a pH indicator, and is also used for the synthesis of several important substances such as paracetamol, phenetidine, and dyes. The hydroxyl group attached to the ring is activated for electrophilic aromatic substitution and presents as results using the same technique of obtained 87 of total yield and mononitrates and 2.3 to 1 selectivity of the para-isomer in relation to the ortho-isomer. I use the same variables studied earlier, but as the substrate is activated, the value of these variables were modified, being present here coded. It can be seen that the ranges used result in varied yields, so much higher than those reported. Regards the preference selectivity of the para-isomer, it was also possible to obtain results 2 to 3 times higher than the axis ones. Even with this one is a slightly lower total yield, but the selective is 80 to 1 para to ortho-isomer. Another example involves the nitration of benzoic acid, a substrate containing an adjuvant group that provides the meta-isomer here as the main product. In this case, the objective was to improve the total meta-isomer yield while minimizing the amount of ortho-isomer. As can you see, the results confirm these improvements. We have 85% and obtain 99% and 97% of yield, total yield, and have the selectivity but much high here. Thus, in conclusion, as can be shown in the 4 examples cited here, it was possible to promote improvements in all processes through the implementation of the proposed methodology. And the focus of the chemical reaction provide positive impact on subsequent stages with reduction and even elimination of steps. The use of design expert software allows the evaluation of the influence of the variables in addition to the visualization of the surface in each study. I think that the graphic possibilities allied to the friendly environment are relevant differentials of this software, which makes me highly recommend Design Expert. My research was not restricted to this case study. I was a design expert a lot, both for product development and process revitalization, like the ones present here. And I also use the results to obtain relations between generated models and physicochemical properties of interest. Studies that I hope to discuss with you at another time. I appreciate the attention given and the support received. It's a pleasure to be able to participate in such a well-organized event. This here is my lab, and I will be happy to receive you in Brazil. And I hope we can establish new partnerships. I regret that the questions be forwarded to my email. And again, thank you, everyone.
Thank you, Erika. We appreciate the time that you've spent with us. As Dr. Chrisman has indicated, she will accept questions via her email address, which is shown here on her slides.